chapter 9, 9B, 9.3b, last part of this chapter. Your test will be next Tuesday. Yeah, Tuesday. Okay, we'll do a review on Monday, test on Tuesday. Yes, ma'am.
Can I get the worksheet early?
Okay, sure. So we're doing De Moivre's theorem today. And De Moivre's theorem says if we have a complex number, and they're using z for the complex number here. If we raise any complex number to a power, if we convert it over to polar coordinates, it's extremely easy to take the power rather than multiplying it out. Okay, think about if we were doing 2a or 2 plus 3i to the 5th power. You'd have to either use Pascal's triangle and FOIL it out and remember all that stuff, or you'd have to do 2 plus 3i times 2 plus 3i times 2 plus 3i and FOIL all that out, combine up like terms, and take care of your I squareds and I cubes and I to the fourth and all that crap in there, and it's a big ugly mess. If you convert it over to polar coordinates, it's actually a very easy thing to do. You take the r in front to the power, and you take the angle theta times the power. That's it. So if you're taking a polar coordinate, if you're taking a complex number written in polar form, it's really very, very easy to take it to a higher power. Okay. So, for example, on the first one that I have here, I want to take this to the 5th power. What's my r in front? It's a 1. So I have 1 to the 5th power times the cosine of 5 times 7 pi over 10 plus I sine 5 times 7 pi over 10. 1 to the 5th is 1, so this gives me the cosine of 7 pi over 2 plus I sine 7 pi over 2. Piece of cake, right? Really, really very easy to do. Rather than taking it if it were a complex number, multiplying it out, be a nasty mess. Okay. So, next one, same idea. Okay. My r in front is the 4th root of 5, bless you. So I'm taking the 4th root of 5, and here's the easy way to do that. Rewrite your radical as a fractional exponent. Trust me, when you get to calculus next year, you don't ever want to work with radicals. You will take almost every single radical you have in calculus and rewrite it as a fractional exponent, because fractional exponents are so much easier to work with. So if I take the 4th root of 5, well, that's 5 to the 1/4 power. And my rule says, oh, I take that to the 12th power. So much easier to work with. And then I have that times the cosine of 12 times pi over 18 plus I sine of 12 times pi over 18. And then 5 to the 1/4 to the 12th power. Well, I have my exponent rules up here. My other class is doing that. So when I raise power to power, multiply, what is 1/4 of 12? 3. So this becomes 3. So I have 5 cubed, so I have 125. Much easier than trying to figure out, oh, if I take the 4th root of 5 to the 12th power, rewrite it as a fractional exponent, makes it really easy to do. Really easy to do. And then I have that times the cosine. And 12 over 18 reduces to 2/3, right? Yeah, 2/3. So I get 2 pi over 3 plus I sine of 2 pi over 3. Now, I forgot the second part of the answer expressed in rectangular form. So in this one, it's really not that hard. It's 125. Cosine of 2 pi over 3 is negative 1/2. The sine of 2 pi over 3 is root 3 over 2. Multiply those times 125. I get negative 125 over 2 plus 125 root 3 over 2. And then let's go back to this one and figure this one out. This one actually is really easy. 7 pi over 2, so it's an odd pi over 2. Let's see, that would be, the cosine of that would be 0. The sine of that would be negative 1 for this. So I get 0 minus I, which is actually negative I for my final answer. I'm sorry, I meant to convert it over.
How did you forget?
Did I forget the I on this one? I'm sorry. I forgot to write the I on that one. My bad. Thank you. Questions so far? It's actually, that part's pretty easy to do. Honestly, it's not bad. So we get to these two here. Okay. Root 3 plus I to the 6th power. This is one where if you wanted to FOIL it out, you could FOIL it out. And you do it again and again and again, and you got radicals in there, and then you got i's and I squareds and all that crap that goes with that. If you wanted to try to use Pascal's triangle, you could do that. It'd be a real mess. But if you convert it over to polar form and then apply DeMoss theorem, it's actually really easy to do. Okay, so polar form. First thing you gotta do is figure out the R. And you get the R on this one is 2. And then you have to figure out what your theta is. So we have on this one, it's the tangent of theta equals 1 over negative root 3. And this one is in the second quadrant. And if you figure that one out, you end up getting theta being 5 pi over 6. Cosine of 5 pi over 6 plus I sine of 5 pi over 6. And I'm taking that whole thing to the 6th power. Yes? R, negative square root of 3 squared plus 1 squared is 3 plus 1, which is 4. Square root of 4 is 2. Sorry, we've done an awful lot of finding the R, so I kind of glossed over that one in this particular problem. You gotta remember, I can't, sometimes I can skip, sometimes I can't. Okay. Then you gotta take that to the 6th power. Well, that's not a problem, right? So I have 2 to the 6th times the cosine of 6 times 5 pi over 6 plus I sine of 6 times 5 pi over 6. 2 to the 6, 2, 4, 8, 16, 32, 64. 5 pi over 6 times 6 is 5 pi, so I have the cosine of 5 pi plus I sine of 5 pi. And then odd pi is out that way. We have 0, 1, 2, 3, 4, 5 pi. The cosine is -1 and the sine is 0. So I have -1 here and 0 for that, which means I get -64. And if you don't believe me in the ease of doing that, go ahead. Take your time on your own and do this. As if it were like x plus 1 to the 6th power, only you've got √3 negative. Go ahead. If you don't believe me, go right ahead. Go right ahead. And then if you take it to a higher power, like 10, you really don't want to do that. You want shortcuts rather than foiling it out. Okay? So I do the same thing on here. This one, actually, your R is really easy on this one. Those are actually points on the unit circle. What is the radius of the unit circle? 1, thus the term unit circle. Because the radius is 1 unit. It's 1. Those are actual points on the unit circle, actual cosine and sine on the unit circle. So your radius, that's easy. I have a radius of 1. My R equals 1. And then I find, yes.
So will it always be 1 if it's any...
If it's particular values that are found on the unit circle, yes, it will be 1.
So not just those exact ones.
No. Yeah. Any unit circle coordinates, grades 1. If you don't believe me, just take, hey, square the first one, square the second one, add them together, take the square root. Yeah, you will get 4 over 4, which is 1. The square root of 1 is 1. Okay. And then, okay, what's the point on the unit circle where I have -1/2 for the y and √3 over 2 for the x? That is 11 pi over 6. So I have 1 cosine of 11 pi over 6 plus I sine of 11 pi over 6, all raised to the 10th power. Well, that means I have 1 to the 10th cosine of 10 times 11 pi over 6 plus I sine 10 times 11 pi over 6. Well, 1 to the 10th is 1. 10 times 11 pi over 6. Well, 6 and 10 reduce by 2. Right, so I get 55 pi over 3. Cosine of 55 pi over 3 plus I sine of 55 pi over 3. Bless you. And then you got to figure out how many times around the circle 55 pi over 3 is. And find a coterminal angle to go with 55 pi over 3. Well, 6 pi over 3 goes around 1 full circle, right? So you divide 55, you subtract 6 from 55 until you get a number less than 5. And you end up getting an equivalent to, and I forgot, it doesn't really matter, but you get the cosine as 1/2. And the sine is √3 over 2. Okay? Once again, would you really want to FOIL that out to the 10th power and try to figure that one out? Even with Pascal's triangle, that's a pain in the butt. Okay? Much easier way to do it. Sometimes it looks nastier, but it's actually easier. Okay. Nth roots. Working backwards. Okay. My apologies for the overlapping. Something I need to get fixed. You can kind of see where it overlaps a little bit. My bad. Sorry about that. I'm going to get it fixed before I got going on this today. So if I want to take the nth root, it's a little more complicated. Instead of taking the nth power, I want to take the nth root. Okay. Well, the R is pretty much the same thing. Took a power, I took the r to that same power. I want to take a root, I want to take the nth root of that power, of the r in front. The interior is a little more complicated, okay? And when you have complex numbers, it's not like you have one particular root. Okay, it's not like you have one particular root. You have several of them. You have several roots that you are working with if you have complex numbers. You're not going to get just one value. It's not like the cube root of 8 is 2. Great, it's 2. But when you have complex numbers, you're going to have 3 separate roots. Okay, that's what we're dealing with here. You're going to have 3 separate roots. Okay. Some real, some complex, depending upon what we're dealing with. Now, we're going to leave all of these answers on this one in polar form, but we will not be doing that on the next example. This one, we'll leave them in polar form. Okay, but you're going to have 3 distinct answers. If you do a cube root, our example here, we're going to do a cube root. You're going to have 3 distinct answers. Okay? Because if you look at it here, your formula is cosine of the angle theta divided by our root that we're taking, plus 2 pi over that root times k. K goes from 0 to 1 less than our root number. N minus 1. If we're taking the nth root, we go to 0 to 1 less than the root number for our value of k. So, this example here, we have the cube root. Taking the cube root, and it's 3. That means we're going to have values of k of 0, 1, and 2, 1 less than the final root. So you're going to have 3 answers. For those 3 answers, k is going to be 0, 1, and 2. So you have to do this 3 times. Once with k being 0, once with k being 1, once with k being 2. Okay, does that make sense? So, looking at this problem here, we're doing the cube roots. That means that n equals 3. Right? Cube root, third root, n equals 3. So, our formula is, we have the cube root of 8 times the cosine of pi over 10 divided by 3 plus, and I got to put this in parentheses, 2k pi over 3 plus I sine of pi over 10 divided by 3 plus 2k pi over 3 for k equals 0, 1, and 2. This is our formula. This is our setup. This is not our final answer. This is our setup to get to our answer. Yes?
How do you found n?
Cube root. What's the cube root? Cube root is the third root, right? That's where n is. Yeah. You have to do the 8th root. N would be 8. Lord help you if you have to do that. Just because you got a lot of iterations of it. Okay, the square root would be 2, cube root is 3, any other root would be n, it's obvious what it is. Okay. So that's my setup. Now, what is the cube root of 8? 2. That's nice, I can do this. So I get, for my first answer, I get 2 here. And this is 4, actually, let's do this. I'm going to do 3 of them, right? I have my first one is k is equal to 0. So I have to do 3 of them, right? First one, k is equal to 0. So I get 2, because the cube root of 8 is 2. Times the cosine. Pi over 10 divided by 3 gives me pi over 30. Right, so this is going to be pi over 30 for all of them. So I get pi over 30 plus 2 times 0 times pi over 3. And you're not going to have to fill it in every time like this, but I want you to see how it's done. I want you to get this down and understand it. Plus I sine of pi over 30 plus 2 times 0 pi over 3. Which means my final answer for this one is going to be 2 times the cosine of pi over 30 plus I sine of pi over 30. Because if I put 0 in the other one, what do I get? I get 0 in my numerator, it doesn't matter. So the first one actually is nice. First one's nice because the second term that I'm taking the sine and cosine out, the second angle becomes 0. But in 0 for k, the second part disappears. Sweet. Okay? Does that make sense? Makes it nice. So that's my first answer. How many more do I have to go? Yay! So I have to do it for k equals 1. I still have the 2 out front. Cosine of pi over 30 plus I put 1 in for k, which should give me 2 times 1 times pi over 3 plus I sine of pi over 30 plus 2 times 1 times pi over 3. Which means I have 2 cosine pi over 30, 2 pi over 3, which is 20 pi over 30, so I get 21 pi over 30. Right? Yeah, 21 pi over 30, which reduces down to 7 pi over 10 plus I sine of 7 pi over 10, because once you do the fraction for the first one, you get the same fraction for the second one. Yes, ma'am. Okay. This is not 21. This is 2 times 1 times pi. Right? Which is 2 over 3. 2 over 3, 1 over 30 from the denominator. How many more answers do I have to do? One more answer. K equals 2. 1 less than our root. So I still have my 2 out in front. Cosine of pi over 30 plus 2 times 2 times pi over 3 plus I sine of pi over 30 plus 2 times pi over 3, which means I have 2 times the cosine, 4 pi over 3, that's 41 pi over 3. Yeah, pi over 30 is what I end up with, and you can't reduce that. 41 pi over 30 plus I sine of 41 pi over 30. Questions? Okay. Solve the equation. X to the 6 equals negative 64, sorry, x to the 6 plus 64 equals 0. What values of x will make that true? It's a very good question, isn't it? Very, very, very good question. Notice it says in the complex numbers, because are there any real solutions? No, because what would be the smallest possible value of x to the 6th? 0. X to the 6th in real numbers, the smallest value would be 0. And it would never be negative because the 6th power means anything to an even power would be positive. So 0 or larger. X to the 6th is 0 or larger. So if I had 64 to 0, I'm never going to get 0. X to the 6th needs to be equal to negative 64 to solve this. I cannot solve this in the realm of real numbers. There are no real solutions. There are complex solutions. I'm solving a polynomial in the complex realm. That's what I'm doing here. Okay, I have a simple polynomial, but I need to solve it in the complex realm. Now, if it's an odd power, you will get at least one real root. If it's an odd power, you will get at least one real root. If it's an even power, you may not have any real roots. In this case, we have no real roots. If you were to graph it, the graph would never cross the x-axis. It would look an awful lot like a parabola, a little flattened out, well above the x-axis. In fact, 64 is as low as it would get on the y. That's what it would look like. So we're trying to solve this. What we're trying to do is we're trying to solve the equation x to the 6 is equal to negative 64. Which means that we need to find the 6th root of negative 64. That's what we're looking for. Okay, so what we have to do is we have to write negative 64 as a complex number. So I need to take negative 64 and write it as a complex number. So that would give 64 times the cosine of some angle plus I sine of some angle. Now I got to figure out what that angle is. It's going to give me negative 64 and only negative 64. So I want to know what angle gives me a negative 1 for the cosine and a 0 for the sine. Pi. If I put pi in here, will that give me negative 64 if I convert it back to rectangular coordinates? Cosine of pi is negative 1. The sine of pi is 0, so I have negative 1 and 0. Multiply that times 64. What do I get? I get negative 64. This is negative 64 in polar form. Now I need to take the nth root. In this case, the 6th root. Okay. So, n equals 6. My r here is 64, so what I'm going to have in front, I'm going to have the 6th root of 64. What's the 6th root of 64? 2. And what are my values of k? Almost 0, 1, 2, 3, 4, 5. 0 through 5. Because you have to have 0. 0 is the easy one.
Wait, how do you get pi here?
Okay. I want to take negative 64 and write it in polar form. So I have to have 64 times 1 plus 0i. Pi is going to give, sorry, negative 1. It's going to give me negative 1 here and 0 there. Negative 1 plus 0i. If I multiply that through times 64, what do I get? I get negative 64. And that's just converting it over. Okay. All right, here we go. So our first root, k is 0. Now, what are we going to have? We're going to have, I'm not going to do this for every single problem. My 2 in front, I've already figured out, 6th root of 64, which is 2. So I'm going to have 2 in front of every one of these. And then I'm going to have the cosine, and it's the angle divided by n. So I'm going to have the cosine of pi over 6 plus 2, in this case, 0 times pi over 6 plus I sine of pi over 6 plus 2 times 0 times pi over 6. Okay. Well, what happens to these two terms here? These are gone because they're zeros. I don't have to worry about those two on the first one. That's nice. Now, what does it say I need to do to my answers? Convert them to rectangular form. So guess what I'm going to want to do as I'm going along? I'm going to want to convert them to rectangular form. So you use your unit circle. Cosine of pi over 6 is root 3 over 2. So I have 2 times root 3 over 2 plus I. And then what do I get? What is the sine of pi over 6? It's 1/2. Multiply that through by 2. I get root 3 plus I. Here's my first root. The first sixth root of negative 64 is root 3 plus I. Hey, how many more times? 5 more times. So I have 2 times the cosine of pi over 6 plus, and I put a 1 in there, that gives me 2 pi over 6 plus I sine of pi over 6 plus 2 pi over 6. Okay, pi over 6 plus 2 pi over 6 is 3 pi over 6, right? Which is pi over 2. So this one becomes, and I'm just going to work here, this one becomes pi over 2. This becomes pi over 2, which is really nice. What is the cosine of pi over 2? 0. What is the sine of pi over 2? 1. So I have 2 times I, so my next root is 2I. See, it's not so bad. Really, actually, this isn't, trust me, you make it a whole lot harder. Okay, so the next one, I have 2 times the cosine of pi over 6 plus 2 times 3, 2 times 2, right? So I get 4 pi over 6 plus I sine of pi over 6 plus 4 pi over 6 equals. Okay, what's pi over 6 plus 4 pi over 6? 5 pi over 6. That makes that nice. That's 5 pi over 6. 5 pi over 6. The cosine of 5 pi over 6, I believe, is root 3 over 2. Negative root 3 over 2. And this one would be 1/2. I distribute the 2 across. I end up with negative root 3 plus I. So this one, k equals 0. This one, k equals 1. This one, k equals 2. This one, k equals 3. Then I should have made that nomenclature first, because otherwise I would have lost my place, which I was starting to lose my place. So I get 2 times the cosine of pi over 6 plus 3 times 2 is 6 pi over 6, which gives me pi. Ooh, that's nice. Although I'll leave it as 6 pi over 6 because it'll be easier to add them together. Plus I sine of pi over 6 plus 6 pi over 6. So that gives me 7 pi over 6 for both of those. Cosine of 7 pi over 6 is the same as 5 pi over 6. Negative root 3 over 2. The sine is negative 1/2. Distribute the 2, I get negative root 3 minus I. Is it flashing to you guys too? Yeah, crap. Just hold it together. I'll erase the board and do it the hard way. It's still holding out. It's not done yet. Don't die on me now. Don't quit. K equals 4. 2 times the cosine of pi over 6 plus 8 pi over 6 plus I sine of pi over 6 plus 8 pi over 6 equals 8 pi plus 1 pi is 9 pi. 9 pi over 6 reduces down to 3 pi over 2. The cosine of 3 pi over 2 is negative 1, right? 0, right. Cosine is 0. The sine is negative 1. So I get 0 here, negative 1 here. So I distribute my 2, and I get negative 2i. All the conjugates. How many more do we have? One more. We can do it. Don't die on me now. K equals 5. 2 cosine of pi over 6 plus 10 pi over 6 plus I sine of pi over 6 plus 10 pi over 6 equals K, 11 pi over 6. Cosine of 11 pi over 6 is positive root 3 over 2. And sine would be negative 1/2. Multiply through by 2. We end up with the square root of 3 minus I. Ooh, look. Every single one of our answers has a conjugate. Exactly the same except for plus and minus in front of the i's. As they should. Because every time you get a solution with an I, whenever you're solving a polynomial, you're going to have its conjugate. They always come in pairs. Always come in pairs. They do. It's one of the rules we have. They always come in pairs. Well, you can, but you better hope that you have, make sure that you do it. But you will have a conjugate for every one of them. So if you are a smart and intelligent person, you could get halfway through and go, okay, now you're going to have them. But however, yeah, those first 3 do match up with the bottom 3 down here, but you just got to make sure you have them in there. But yeah, if it's an odd root, if you have an odd root, like you're doing a cube root or a fifth root, you will have at least one real in there, and you got to make sure you get that real one in there too. But if you have an even root, they always come in pairs, and you may or may not have imaginary numbers or not, depending upon what you're starting with. This one we were guaranteed to have them all be imaginary, but that is not always the case. Any questions? This will probably be the hardest thing to remember for your test.